So in our last lesson, we looked at all the different names if we were up to 4 legs, 4 electron groups around a central atom. Now we're going to look at the different names of shapes when we're beyond 4. But let's kind of review, okay? If we had 3 groups, one of them could be a lone pair and it was just bent. If there were 4 groups, if one of them was a lone pair, then we had a trigonal pyramid. If 2 of them were lone pairs, it was back to bent. And that's all that we had for that. Now we're going to go when we have 5 groups around the central atom based upon a trigonal bipyramid and 6 groups around the central atom based upon an octahedron. And there's a whole lot more choices of names, but we want to get ourselves familiar with what they look like so that it makes sense how they are named, what they are named, okay? I want you to do the electron geometry of Sf4, okay? So what are you going to do? You're going to stop the video, you're going to do a Lewis structure, you're going to figure out how many legs it has and give it an electron geometry name, electron pair arrangement. Remember, we were focusing on the electrons. Once you have done that, then we'll resume. Okay, so you should have come up with the fact that this was a trigonal bipyramid. And if you did, we're in good shape. But we're going to finish that problem together. So what does a trigonal bipyramid look like? You had your sulfur, you had a leg up and a leg down. Those are the axial positions. You have one in the plane, one coming out at you, and one going back. These 3 are the equatorial positions. So 5 legs trying to get as far apart from each other is this arrangement called a trigonal bipyramid. And that's all you know so far. Now we have to figure out, okay, we've got one of those is a lone pair. 4 of them are atoms. We have 4 fluorines on here. One of them was a lone pair. And let's just, you know, when you drew your Lewis structure, I hope it looked like this. I better get it up here just so you've got it correct in your notes. Okay, let's get it up here. And there's an extra lone pair on that central atom. So there is Sf4. We had done the Lewis structure of that way back when we did Lewis structures. So we have 1, 2, 3, 4, and a lone pair 5. That's the 5 legs. That's the trigonal bipyramid. Okay, so let me pick up a trigonal bipyramid. This is the one geometry where the legs are not all equal. Okay, these arrangements, we've got these 3 in the middle with 120-degree bond angles. Okay. We've got these guys above and below, these axial positions, where we have a 90-degree bond angle. If we put a lone pair here, okay, we're just going to figure out our choices. If we put a lone pair here, then we would have an atom 90 degrees from that lone pair in 3 locations. 90 degrees is very tight, okay? It's a very tight bond angle. So putting a lone pair here, you have 3 atoms that are 90 degrees from it. Now if I put one here, a lone pair here instead, then it only has 2 that are 90 degrees from it. And these guys are much, much further away. Okay, those are 120 degrees. So these are roomier positions. So whenever you put lone pairs onto this trigonal bipyramidal shape, you always put them in the equatorial position. Remember the equatorial position? They're like the equator. You always put them here. You do not put them in the axial position. Now I have these 3 to choose from. I've got to put one lone pair in one of these 3 locations. So let me turn it this way. Are one of those more roomy than any of the others? No, they're all the same exact distance from each other and from the position above, and I mean this one here, these axial positions. So it doesn't matter which one of these 3 I choose. So I will pick one. I will pick this one. Okay, so this is what I have. I've got a lone pair, and if I match it up with the way I've drawn it, I've got my lone pair here, and then I've got the other 4 locations with atoms. So we'll draw that in. I'm going to put my lone pair here. Okay, there's my lone pair. The other 4 legs are going to have my fluorine atoms. And now, trigonal bipyramid is the electron arrangement, okay? And we answered that with when you stopped the video. That's the electron arrangement. Now we've got to give the geometry, molecular geometry name. Now this is the best name of all. I want you to imagine this sitting out on the playground, and one kid sitting here, and one kid sitting there, and they're doing this. What did you call that? Okay, you might have called it a teeter-totter. This is not a teeter-totter. This geometry is called seesaw. Believe it or not, that is the name of this. Now, I have seen textbooks that try to get fancy with this name, and they call it a distorted tetrahedron. Yeah, that's pretty distorted, okay? But I love the name seesaw. It really describes what we see. So that's the base of the seesaw. One person would sit here, one person would sit here, and they could teeter-totter, seesaw, back and forth, okay? So that's the name of that. Let's think about bond angles, all right? This was 90 degrees. So now it's less than 90 degrees. This was 120 degrees. So now it's less than 120 degrees. So when we describe the bond angles, that's what we have. And then we've got this angle from all the way up here. It was 180. Now it's going to be less than 180. Okay, everything gets distorted a little bit, but that is the seesaw. So now we have got the five legs. That's a trigonal bipyramid electron arrangement. One of the legs, and it goes in the equatorial position, is a lone pair. That gives the name seesaw. Let's move on. There is the shape. Okay, we see what it doesn't do. It's not in the axial position, but it's in the equatorial position, and you have now in your notes why that is. So the next one we're going to do is IF3. So let's put my model down, and let's do a Lewis structure of IF3. We know that I is the central atom. We know that it's surrounded by fluorines. Okay. We go and count valence electrons. I has 7. Each fluorine has 7. That is 7 times 4, 28 electrons. Okay. So we start putting them in, starting with single bonds, 2, 4, 6, moving out here, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Now everybody has an octet, but I have to use 2 more. So I'm going to put them also on the central atom. And now I've used 28. Now I'm ready to count my legs. How many legs does this thing have? Okay. It's got 3 bonded atoms. That's 3. It's got 2 lone pairs. So it has 5 legs. So it once again has an electron arrangement that is a trigonal bipyramid. Okay, so that is its electron arrangement. So let's draw the 5 legs. We have I, we have the 2 axial positions, one above, one below, the 3 equatorial positions that are in a trigonal plane, okay, and that's our trigonal bipyramid. Now we have to figure out where the lone pair are going to go. So with this one up here, we knew we had to put it in the axial position. Now, I could choose this one where there are 2 90 degrees from it, okay? That's pretty tight. I guess it's easy. What can I say? Boom, boom. Oh, and this lone pair over here, which needs a lot of room, and that's not good. So putting it right next to a lone pair is never a happy state. This is right next to it, but it's further away, right? So this is 120-ish away from these lone pairs, where this is only 90-ish away from those lone pairs. So it again will choose an equatorial position, and it will always do so. Okay, when you put lone pairs into a trigonal bipyramid arrangement, you always put them in the equatorial position. Okay, so this is what we have, and I want to hold it like this and draw what we see here for a reason. We'll see why here in just a minute. So I'm going to put lone pairs here and here. That's where it represents this lone pair and this lone pair. Okay, and then the above, the below, and the one going off in this direction is going to be atoms. What were the atoms? They were fluorines. Okay, so I'm going to have this be a lone pair and this be a lone pair. So those are my lone pairs. And then I've got my F, and my F. So now, The electron arrangement is still trigonal bipyramid, but now let's give it a name of the geometry, the molecular geometry. Let's come up with a good name for this guy. Now what they came up with is to think about the alphabet. All right, what letter of the alphabet, if you're only focusing on the atoms themselves, what letter of the alphabet do you see? Okay, this is called T-shape. This is the T-shape, okay? That is actually the name of this molecular geometry, T-shaped. All right, so this is a T on its side, sitting here like this. T-shaped. And what's the angle? Well, it was 90, so this is less than 90 degrees. And that is what you would call the geometry, what you could tell me about the angles, and it's all based upon a trigonal bipyramid electron arrangement. All right, let's do this next one after I clean off my board. Okay, so we're ready to do XeF2. With XeF2, we have, well, let's go ahead and count valence electrons. Xenon has 8, each fluorine has 7, that's 14. That's 22 electrons to work with. I connect them with single bonds, that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. The octet rule is satisfied for everybody, but I was supposed to use 22, so I have to put another pair on the xenon. So now if I'm going to count those electron groups, or what I call legs, okay, how many legs does it have? It has 2 atoms and 3 lone pairs, that's 5 legs. 5 legs is always the geometry, electron arrangement geometry called a trigonal bipyramid. So I have 3 like that, 1 coming out, 1 behind, where these are my axial, these are my equatorial. Now when you do a trigonal bipyramid, you always put the lone pairs in the equatorial positions. So I have 3 of them. I have 1 here, I have 1 here, and 1 coming out at us, those 3 there, and then we have the fluorine here and the fluorine here. So while the electron arrangement is called a trigonal bipyramid, and I drew a big trigonal bipyramid to get me there, I only look at the atoms to get the geometry. So the molecular geometry, which is our final goal, has a name. We have seen this name before. 3 atoms in a straight line is called linear. And the bond angle is not distorted by these. If we look at what we have here, and I'll go ahead and remove this last one. So we've got the 3 lone pairs in the equatorial position, and we have these guys here. These are affecting the bonds equally all around, so it can't distort it, and we still will keep 180-degree bond angles for this guy. So that is the only possibilities of shapes based upon a trigonal bipyramid. Let's kind of think about them all one more time. We had where all of them were atoms, okay, so if we put another one here, which I don't, yeah I do, I'll steal one from here and put it on. If all of them were atoms, it was a trigonal bipyramid, but if we put 1 lone pair, we had the seesaw. If we had 2 lone pair, we had the T. And if we have 3 lone pair, that's what we just have right here, it is linear. If we put another lone pair, we just have 2 atoms, and that's always linear, and we don't need to do anything in order to do work for 2 atoms. So there we have all the different geometries when we had 5 legs around it. Okay, now I would like for you to do this. I want you to determine the electron geometry, the electron arrangement about BRF5. So what you're going to do is you're going to draw a Lewis structure, and you're going to see how many legs it has and decide what its foundational beginning electron geometry is. Did you come up with an octahedron? If so, that's great. That's what it is supposed to be. So it's supposed to be an octahedron. Now, if you didn't come up with that, let's see if we can figure out why. Where did you go off? Br with 5 fluorines around it. If you count up the number of valence electrons, we have 5 fluorines and a bromine. All of those have got 7 valence electrons, so 7 times 6 is 42. When you give everybody its octet, as you would want to do, then what you will find is that you have an extra set that you need to put on the bromine. So we have 5 atoms, we have 1 lone pair, we have 6 legs, and 6 legs is an octahedron. So we put the Br in the middle, and we draw an octahedron. Octahedron has 1 above, 1 below, and 4 in the plane surrounding this central atom. Okay, so that is the electron geometry called an octahedron. Now we have to decide where the lone pair is going to go. So we take our octahedron, which I have right here, and we consider its geometry. All sites are equivalent. Every one of these locations has exactly the same number of atoms, 90 degrees to it. They have 4. This guy has got 4 guys, 90 degrees. This guy has 4 guys, 90 degrees. All sites are equivalent. So it doesn't matter where the lone pair goes, so I'll just pull one off. So I've taken this one off. Now I'm going to hold it like this, okay, with my lone pair below, and then we've got these 4 that are in this plane, and it's the one above, and I'm going to put those in on my drawing here. So my lone pair was down at the bottom, okay, and each of the other legs are being housing the fluorine. So we have the fluorine, a fluorine, a fluorine, a fluorine, and a fluorine. Now we have to give this molecular geometry a name. Molecular geometry. I want to ignore this lone pair so much that I want to pull it completely off. It's holding that location, it's holding this shape, but let's consider what we're seeing here. Do you see this little base? It's a square base, right? And it's a little pyramid sitting on a square base. So the name of this geometry is called square pyramid, or square pyramidal geometry. And that would be the name if you've got one lone pair. All right, so there is what it looks like on the image on the screen. On the left is our Lewis structure. In the middle, they're showing you the lone pair there. It's holding one of the legs of the octahedron geometry, but remember, you ignore it, and maybe that's a neater drawing than what you've got in your notes there, but you've got that trigonal base, that square base, and it's a little pyramid there, so it is a square pyramidal geometry. All right, we're ready for our next one, Xef4. I am going to draw the Lewis structure of Xef4. So we have Xe, we're surrounded by 4 fluorines. Okay, we count up valence electrons. Xenon has 8 because it's a noble gas. Each of the fluorines is 7. 7 times 4 is 28. And we add those up, we have 36 to work with. We do 2, 4, 6, oops, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, because I have to put them on the central atom. So now I count legs. I have 4 atoms bonded. I have 2 lone pairs. I'm back to 6 legs. I'm back to the octahedron electron arrangement. So I will draw the xenon, 1 above, 1 below, and the 4 in the plane, 2 coming out at me and 2 going back behind. Now we have to decide where am I going to put those lone pairs. I chose on this model to show it on the bottom. So let me go ahead and just show it on the bottom, okay? So I have a lone pair taking up that leg. Now the lone pairs need as much room as they can get, and they need to be as far away from any other lone pairs as I can make them. So for this one, if I'm trying to make them as far away from any of the lone pairs as I could get them, they're going to go across from it. So I'm going to put this. And then the fluorines are going to take those 4 legs. Okay? So that's what we have right there. And let's give it a name here in just a moment. There it is. Okay? I've chosen lone pair below, lone pair above. Now the lone pairs are there. I've just kind of removed the atom and the legs. There's a lone pair above, a lone pair below. But I just wanted to look at what you have here. I have 4 atoms. They are all in a plane, and that is a square shape, right? That looks like a square. I don't know how we want to look at it to make it look like a square to you. But this thing is called a square plane or square planar. Okay, that would be what this is as far as its molecular geometry. All right, so the next one, and there's the picture of that. I just want to talk through the possibilities of one more shape from this. Let's imagine that we did all of this work and we had 3 atoms and 3 lone pairs. It would still be based upon a tetrahedron, an octahedron. So I'll put my octahedron legs back in. If we had an octahedron and we had 3 lone pairs instead of 2 like this one, where would we put the next one? Okay, so we have them across from each other. That's this one and this one, so I've got them across from each other. Now I have these 4. Of these 4, is there any one that's roomier than the others? Well, no, they're all equal, so it wouldn't matter. So I'll take this one off. Don't want to take it off on that end, I want to take it off on this end. Okay, so that's taking it off. Now let's just look at the atoms only. If we look at the atoms only, do we know the name of that shape? What is that name? That's a T. So if it's an octahedron with 3 lone pairs and 3 bonded atoms to that central, it's an octahedron, but we'll call it a shape of a T shape for its molecular geometry. And then the next possibility is to say, okay, now I don't have 3 lone pairs, but let's go to 4 lone pairs. Where am I going to remove that 4th one? Well, it's going to be across from this one. And we've already heard of the name of that shape. What's the name of that shape? It's linear, straight across. Okay, so once you get to the octahedron and you've drawn an octahedron and you start putting lone pairs in, put them across from each other, then remove one and that gives you a T, put it across and that gives you linear, and that's all the shapes. We don't have repeats, any more new names for any of our shapes. Okay, what do we have next? The next thing that we need to do is consider that if there's more than one central atom, okay? Multi-central atoms. You can do a Lewis structure for something that has more than one central atom, and you can do a geometry for more than one central atom. So we're going to do it for CH2, CH2, after I get some help erasing my board. So now we're ready to do CH2, CH2. So we got more than one central atom. So we have a carbon connected to a carbon, and each carbon has a hydrogen connected to it. Now this is not a Lewis structure yet. We have to make sure we count up valence electrons. So each carbon has 4 off the periodic table, and there are 2 of them, so 4 times 2, that's 8 for the carbon, and each hydrogen has 1, so I'm going to have 4 more, and that's 12 to work with. I've already drawn in 2, 4, 6, 8, 10. This carbon is deficient, so now it has its octet, and I've used the 12, but this carbon is not happy, so I will shift from an external in, okay? So that gives me a double bond. None of my examples, well, maybe one, have had a multiple bond, but this is what we do when we do a geometry. We do not do a geometry for the entire molecule. What we will do is talk about the geometry at each central atom. So let's do this one first. I'll call this carbon 1 and then this one carbon 2 and talk about the geometry. So at carbon 1, what does it have? It has 3 atoms bonded directly to it. 1, 2, 3. So it has 3 bonded atoms and it has no lone pairs. What is the name of a geometry with 3 legs? Well, that would be a trigonal plane. Okay? So there's the carbon connected to a hydrogen, and the other carbon. And what we would say is at carbon number 1, it is trigonal planar. Happens to be a double bond, so I could show it as a double bond, but doesn't change the fact that it's trigonal planar. And then I look at carbon number 2. At carbon number 2, what do I have? I have 3 bonded atoms. I have no lone pairs, so I have 3 legs. 3 legs trying to get as far apart from each other as they possibly can go is a trigonal plane. So it is a trigonal plane here as well. So when you're asked to do the molecular geometry, when you have more than one, you would state what the geometry is at each central. So it is a trigonal plane at carbon 1, and it is a trigonal plane at carbon 2. And if you had lots of atoms joined together in a very complex structure, that's what you would always do. You break it down and you don't have to worry about the full complex structure. You're just looking at it one central atom at a time. All right, so that concludes everything I wanted to tell you about geometry. I want to kind of recap before we leave this lesson. If you're asked to do a molecular geometry, start with a Lewis structure, okay? Draw that electron arrangement. You only have 5 electron arrangements that you need to practice drawing. You've got linear, you've got a trigonal plane, you've got a tetrahedron, okay, that's 1, 2, 3. You've got a bipyramid, that trigonal bipyramid, and you've got the octahedron. If you could practice drawing just those 5 shapes, then you could come up with the molecular geometry. Linear, a trigonal plane. If you cover up one lone pair or ignore one lone pair, you are bent. A tetrahedron. If one of them is a lone pair, it is a trigonal pyramid. If 2 of them are lone pair, it is bent. You've got a trigonal bipyramid. If one of them is a lone pair, it is a seesaw. If 2 of them are lone pair, it is a T. If 3 of them are lone pair, it is linear. You've got a octahedron. If one of them is a lone pair, it is a square pyramid. If 2 of them are lone pair, it's a square plane. If 3 of them are lone pairs, we have a T shape. Can you see that T? If 4 of them are lone pairs, then it is linear. So those are the names, and you could practice drawing those 5 shapes, erasing and naming, and you could do the geometry of everything without just a memorization of a table.